In this video, we give a brief introduction to functions of several variables. So this is the first of two videos for Chapter 13. And really in this video, I'll cover 10.1 and 10.2. A lot of this you'll cover again if you continue on into Calc 3. But I just want to give a little crash course, and then with a main focus in section 13.3 where we work with partial derivatives, okay? So first, what I want to say here is many functions in mathematics, and especially in the real world, we live in a three-dimensional world. We have to describe our world mathematically and do it accurately, right? So instead of just y equals f of x, right, we better be able to describe a point in space with x, y, z type coordinates. And just a quick example of where this might show up, right? We've been working with volumes a little bit. So say maybe the volume of a box or the volume of a cylinder. Each of those is a three-dimensional object, and their volumes should have three variables in them. The volume of a box is like length times width times height, and the volume of a cylinder is like pi r squared h, right? So we have these three-dimensional functions already. We just don't necessarily have a nice notation to write them in, and how to work with them in a calculus sense, how to analyze them, look at slopes, rates of change, derivative, mins and maxes. That's basically the premise of what you'll look at in Calc 3, and this is just kind of a brief introduction. The notation for a multivariable or several variable function, say for example, I'm looking at volume here, say for our box there, it's a function of length times width times height, right? That's just it. We would say that V is F of LWH, right? And that's equal to then LWH. But I think you're slowly getting the idea here. We can evaluate this at a given length, a given width, and a given height. And then we would find the corresponding volume. Okay, some other quick examples are z equals f of xy is x squared plus xy. So this function is a function of x and y, and you get out from it like a z value. You can think about z as being like a height. Okay? Now, not always do these correspond to some graphical system necessarily. Functions of three or more variables tend to be difficult to draw or graph. But they still make some sense. Like say, for example, a weather pattern might be a function of the time, the longitude and latitude, temperature. There's a lot of things going on there, and it might not be an easy picture to actually plot like we would, a regular one-dimensional function. And then some other ones, say W, we've already kind of used X and Y. And if Z is to be included, then we have to find some other letter, right? So just W, pick one, is a G. So G, some other function name of X, Y, and Z is maybe X plus 2Y minus 3Z. Huh? So they look very much the same. You can still kind of they look kind of polynomial-like. They're not really called polynomials. They have kind of different names and different things going on. But there's just some examples of functions of several variables, okay? If we want to talk about these functions with respect to, in a calculus sense, domain is kind of one of the first things that we come up with. What's the domain of a function of multiple variables? And we have this definition. We say if for every x and y in the set D, there is a corresponding corresponding real number, I need to say, f of xy, then we say f is a function of x and y, and D is the domain of f. Okay, so for example, I have a function here, f of xy is a quotient. Here I have in the numerator square root of x squared plus y squared minus 9, and in the denominator I have x. And I want to think about what the domain of this function would be. Now, of course, in that denominator x, we can quickly say that I can't have x be 0, right? I can't divide by 0. So that's really the first thing that I can pick out, the pretty obvious thing that does not exist in my domain. So it doesn't matter what y is so far, but if x is 0, then that is outside of my domain. Okay. Also, I have a radical in the numerator, right? So my numerator has some stipulations as well. I know what's under the radical has to be bigger than 0. And that looks a little familiar, x squared plus y squared. If I move the 9 to the other side, x squared, that's the equation of a circle, right? And that's a circle with radius 3. Now, the greater than or equal to implies that my domain has to be outside or on the boundary of that circle, right? So if I draw some coordinate x's around this, and x and y here, that circle, anything inside it is no good, is outside of my domain. My function will not have any values, any kind of height values, any z values outside, on the inside of this circle or on the y-axis, right, when x is 0. But outside the circle, we're good. My function will have values out here, just not inside or when x is 0 on the y-axis. So I've colored that in red as well. And I'll try to outline this a little bit in the next slide here, but it's going to be difficult to see. I don't have a great three-dimensional picture of this function. I was struggling to find one just because it's a harder function to graph. There's a lot of stipulations. But so there's the domain, basically things that are not when x is not 0 and when x and y, x squared plus y squared, are bigger than or equal to 9. We can also evaluate these multivariable or three-dimensional functions at points, right? We can plug in points the same way we would with a one-dimensional function. So what happens here is I take f, and for x and y, I'm plugging in 3. And all that is just take x and y and replace them with 3. And in the numerator, I see 3 squared minus 3 squared, 3 squared minus 9, plus 3 squared is the square root of 9. And in the denominator, I have 3. Well, that's 3 over 3, which is 1. So we can say the function value when x and y are 3 and 3 is 1. And I can plot that then in three-dimensional space as an ordered triple. Right? That there's what we call an ordered triple. Because it's got an ordered, there's 3 coordinates there, x and y and z. Now I've shown here what the xy coordinates 3, 3 are. So basically what we've got going on is at that point, my function is actually at a height of 3, and I can't really draw that here very well. But think about this point here being off of that flat surface, off of the screen, kind of coming out at you 1 unit. Okay, and I'll try to draw that here on the next slide. So what I've got is my function here. I'm going to drop in a picture. This is something that I got from Desmos. It's not exactly, like I said, an easy thing to find, and you're seeing those vertical, this stretching looking thing of my, what we really have here is a surface. We can't call it a curve because this, for every x and y that are in my domain, I have a corresponding z or a corresponding height value. Okay, and what that looks like is a surface. So what's going on here is we see kind of where that circle is down here where things are outside of my domain, right? Everything inside that circle is outside of my domain. Everything else is a little bit difficult to see, but for example, if I were to pick some xy coordinate, xy, so say for example the coordinate, I don't know, we think about usually this guy being the x direction, this guy being the y direction, and the vertical then is being like the z direction. I can plot the point that we had before. It's going to be a little bit hard to see. But for example, 3, 3, 1, 3, 3, 1, I can think about as being kind of like right somewhere in here, not inside the circle. Sorry, that's poor arrow placement, but somewhere just kind of outside, right? You see that little orange dot there? That little orange dot, somewhere just outside of that circle. Because that circle, remember, has a radius 3, so it should be just kind of outside it. And then it's up, it's kind of on that surface at a height of 1. Okay? So, of course, you can try to sketch a surface for any function of x and y. Try to find their domain. What we'll be interested in is finding derivatives. Okay, that's kind of what my goal here is to show you. This video is just an introduction. And to get to derivatives, if you remember way back, derivatives in Calc 1 were a limit definition, right? So I also have to have a limit definition here and several variables, okay? So just a quick bit about limits and continuity. We're not going to spend hardly any time on this at all. Let's just take, for example, the limit here now as xy approaches the point 1, 2. This is a little weird, right? Instead of x approaching 0 or infinity or 1 or 7, we've got both x and y approaching a point. Now, when you get into several variables here, you'll see this if you continue on into Calc 3. But you can kind of approach, you can have x and y approach any point pretty much, but also you can have x approach a point and y kind of stay still. There's lots of possibilities here. And just some general function here. I have a quotient 5x squared y divided by x squared plus y squared. And I want to know what this limit is. Is there any reason why I can't plug in the point 1, 2? 1 for x and 2 for y. I have x squared plus y squared on the bottom. So if x and y were 0, this would probably be bad. In fact, that's likely the interesting case. But really, plugging in 1 for x and 2 for y, I shouldn't have any issues. So this is indeed a direct substitution case, right? We hopefully are able to evaluate our limits that way. Most of the time we're looking for the exciting indeterminate cases. This is not one. I just wanted to show you maybe some notation dealing with a limit of several variables here. So of course that limit shouldn't just be 2. And we can say that f of x, y here, which is this function, I'll just copy it down again, is continuous, right? This function is continuous at xy is 1, 2. At that point, because the limit of xy, f of xy at that point is the function value. I'm able to just direct substitute, plug in that point, and it's the same thing as taking the limit, right? So that's what it means to be continuous. We also hope to find a definition for differentiability, right? That will come in the next video. There's a practice module set up for this chapter already, and I just have 1 or 2 questions to ask you based on this video's material. Can you plug in a point? Is really all I'm looking for. Okay, thank you for watching.